Moore's law is the observation that, over the history of computing hardware, the number of transistors in a dense integrated circuit doubles every 2 years, meaning that every 2 years, computers become twice as powerful. This is because processing power is determined by the amount of transistors that can fit in a dense integrated circuit. While Moore's law hasn't been too accurate in predicting the amount of transistors we are able to fit, current microchips are able to have about 1 billion transistors. Transistors make up logic gates, and logic gates are used in computers and digital electronics. A transistor is a switch dependent on whether or not there is a current flowing into the base of the transistor. An NPN bipolar transistor has 3 terminals, which we call the collector, the base, and the emitter. The current which determines whether the switch is on or off flows into the base. So when the current flows into the base, the transistor is turned on and current is allowed to flow from the collector to the emitter. A PNP bipolar transistor is different in that the current flows from the base instead of to the base to turn the transistor on. Also, current flows from the emitter to the collector instead of from the collector to the emitter. The reason why these transistor switches are important is because computers use binary, which is composed of only ones and zeros. Instead of the base 10 system that we use, the place values for binary are powers of 2. This means that the number 2 in binary is actually 1, 0. A 4 in binary is 1, 0, 0, and an 8 in binary is 1, 0, 0, 0. We can set up electronics to speak in binary by considering the current as 1 and the lack thereof of current as 0. Using transistors, we can set up logic gates which are used to perform complicated tasks. The most basic of logic gates are the OR, the AND, and the NOT gates. The AND gate consists of 2 transistors that both need to be on in order to allow current to complete a circuit. We can represent this relationship using a truth table. Similar to an XY chart, we can input a value of on or off to discover what combinations make an indicator light turn on. For this logic gate, the truth table reveals that the A and the B resistor both need to be on for it to work. This makes even more sense when the transistors are thought of as switches that allow or don't allow current to pass through them. A schematic look at the gate looks something like this. Using a breadboard that allows us to make simple circuits much easier, we can build the gate.
Alright, so our switches just died on us, but it's still the same basic principle. This is an AND gate, and that means that both of these buttons have to be pressed in order for there to be a light. So if I press just one of them, nothing happens, but if I press both of them, the light turns on. Now, so this is a basic schematic of what's going on here. So essentially, we have 2 switches / buttons going to the gates of the bases of the transistors, and the transistors determine whether or not the LED shines. The reason why we have 2 resistors before the bases of the transistors is because if you send too high of a current into the transistor, you can kill them. So we have 200,000 ohm resistors right there, and essentially the current has to go through here into the diode, and it has to pass through both transistors in order to make it to the negative terminal. And the only way for the transistors to let current pass is to send 2 currents through these transistors.
For an OR gate, the almost opposite is true. Our truth table shows us that the A or B switches have to be on in order to complete the circuit, hence the name OR gate. As you can see in the schematic, the current has 2 options for completing the circuit, and each one has a transistor. Each path will complete the circuit. Once again, this is what the gate looks like on a breadboard.
Alright, so this is our OR gate. Now what happens is when we hit one of them, it turns on, and we only need to hit one of them. We can hit both of them and it turns on, and that's essentially what an OR gate is. Now here's the schematic for what we just did. Essentially, there is a resistor, a diode, current flows through this, but to complete the circuit, it has to go through it has to go through this transistor, or it has to go through this transistor. So these are in parallel with each other, and all it takes is to open one of these in order for the circuit to be complete. So we have 2 switches going into both of these transistors, and that's essentially it.
The NOT gate has an inverting effect on the on or off position. This table shows that if A is on, there's no power, but if it's off, current can flow. Here's how it looks on the board.
So what we just built here is a NOT gate. Every single time we hit the button, the light turns off. So it essentially is an inverse of whatever you want. This is a basic schematic of it. Essentially what happens is the current goes through, gets dropped by this resistor, or the voltage gets dropped by this resistor, and it has the option of either going through the diode or going through the resistor, or the transistor, I mean.
AND, OR, and NOT gates can all be combined to create multiple types of simple systems. A simple adder, for example, combines all three of these gates and looks something like this.
So what this logic function does is it gives us these results. If we say 0 plus 0, we get 0 at the end. So if A was 0 and B was 0, we'd end up getting 0 at the sum. And if we had A as 1 and B as 0, we'd also get the answer as 1. And the reason why 1 plus 1 is 0 is because we need a carry function. This is just a very, very simplistic adder. What happens is, so this is binary, right? So it would be 1 plus 1 is equal to 2. However, because it's binary, it would have to be 1 plus 1 is equal to 1, 0. So that's why the answer is 0, because we're only dealing with the ones place. So we're only dealing with that. We need a carry function that'll take care of the 2 and make it 1, 0. So that 0 is that 0.
So here's what our adder looks like. So basically what is, the blue button here is our A input and the yellow is our B. So if we put an input of 1, 0, or 1 plus 0, we get 1. Then if we do a 0 plus 1 input, 0, 1. And if we do a 1, 1 input, we get over into our carry function that gives us our 1, 0 number, or 2, 1 plus 1. Now if we were to break down this adder into a circuit diagram schematic, here's what it would look like. Have our battery. This is our carry function, this dotted box. And then eventually we get to our sum with our indicator light. And the carry will also give us our carry light when we do a 1, 1 input.